In this video, I would like to speak about the sample size based on population proportion. First, let us define what is the population proportion. And to do that, look at this. The prevalence of breast cancer was reported in a paper by Dr. Ahmed and his colleagues in 2010. And this is a quote for the digital object identifier. If you would like to retrieve the full manuscript, and they reported that the prevalence of breast cancer in their specialized breast clinic was 34%, and benign breast diseases was 66%. In another study, Professor Ahmed Mohamed Hassan, late Ahmed Mohamed Hassan, alayhi rahmatullah, in 2008 he published a paper. Also, here is the digital object identifier if you would like to retrieve the whole manuscript, about gastric cancer. And he and his colleague reported that the percentage of gastric cancer among all tumors they have received, not only GIT tumors, but all tumors they have received, the percentage of gastric cancer is 4.5%. And in another paper published by Mr. Hassan Bashir, a surgeon, in 2010 in the Sudan Journal of Medical Sciences, about the surgical site infection in open cholecystectomy. He studied 100 cases. The vast majority of these cases were performed by the surgical registrars during their training program, and he reported that the rate of infection was 9%. So from these examples, the proportion is the incidence or prevalence or frequency of a disease or one of its major outcomes. It is usually found in written paper from the same community or the same society or the same population, or from similar setting from other countries. If we do not find a study, we can literally use the figure 50%, the proportion is 50%, because it gives a very wide variation, and it gives a high sample size, and it gives good power for the calculation of the study. So we have two chances: either to find a proportion from a study in a form of incidence, prevalence, or frequency, or just to quote liberally the figure 50% proportion. Now, let us speak by examples and how to calculate the sample size using the population proportion. And let us start with a very simple example of Mr. Hassan Bashir, a study in Ibn Sina Hospital for the rate of infection in open cholecystectomy. As I said, the vast majority, over 60-something%, were performed by the surgical registrars during their training program, of course under supervision. The surgical site infection was 90%. Then what is the appropriate sample size for a study on surgical site infection? What is the appropriate sample size for a study on surgical site infection in cholecystectomy amid war or without war during the safety period? How to calculate this? Either we use this figure or we use 50%. We are going to use the Cochrane's formula. The Cochrane's formula for calculating the sample size using the population proportion is very simple. This sample size is equal Z value square. And in the last video, I talked a lot about the Z square, and I said for a confidence interval or confidence level of 95%, the critical value of the Z value is 1.96. This is fixed for 95% confidence. So we square it. And the proportion from Mr. Hassan paper is 9%, which is written as 0.09. And to remind you, 0.09, to remind you, we said 1 is equivalent to 100%. And half this one is 0.5. 0.5 is equivalent to 50%. And 5% is equivalent to 1 is equivalent to 100, and 0.5 is equivalent to 50%. 0.05 is equivalent to 5%. 9% will be equivalent to 0.09. So the figure P here will be 0.9 multiplied by 1 minus 0.9 divided by A square. A is the margin of error square. The margin of error, we are going to choose it according to the precision we want. Commonly, it is used as 5%, but we can use it 5%, 4%, 3%, or 2%. And you see in the denominator, if we are using the smaller figure, they will be the bigger the sample size. Okay. So now here we have two figures. We know we can choose margin of error, and we know 1.96 is the Z value. P is the proportion. We get it from the study, or we can get it as 50% liberally, 50%, because it gives wide variation and it gives very high sample size, very big sample size. You see, it is in the numerator on the top. If it is 50%, it will give, the calculation will give a very big sample size. So if we replace the figures, it will be 1.96 squared multiplied by P, which is 0.09, multiplied by 1 minus P, which is 1 minus 0.09, which is 0.91, 0.91, and divided by the margin of error. If you consider it commonly 5%, it is 0.05. Squared means 0.05 multiplied by 0.05. And we continue. Although the total population studied by Mr. Hassan were 100 cholecystectomies, the Cochrane formula we are using does not use a limited number, finite number. It is meant for very huge number of population, for infinite population. In spite of this, we are going to use it, and at the end, we are going to use the 100 to make corrections for the finite, for this very small number. It is called finite population correction, limited number correction of the population. So this is the formula once again, and we are using the z-value, which indicates we are using our formula with 95% confidence level. Z-value is 1.96. We square it and multiply it by P, either from this study 0.09 or 50%. And for the total number studied by Mr. Hassan, we leave it aside for the correction later on. When we come for correction, we use it later. But now we use it as if we are working in an infinite population, in a very big, in a very huge population. So if you look at the bottom line, it is 1.96 squared multiplied by 0.9 multiplied by 1 minus 0.9 divided by the margin of error squared, which is 0.05 squared. And if we continue the same figures, if we continue with the red figures with the proportion multiplied by 1 minus the proportion, 0.09 multiplied by 1 minus 0.09 will be 0.09 multiplied by 0.91, and this will be 0.819. Now the z-value 1.96 squared, it is 1.96 multiplied by 1.96 will be 3.8416. We multiply these together and we divide them by the 5% square, which is 0.05 squared. It is 0.05, 2 decimals multiplied by 0.005 2 decimals, and that will be 0.0025, and the result will be 125.84. And since there is no fraction of a patient in the sample size, we round it up. Look at the sign here, it is not two parallel lines, a little bit wavy lines. It is around about 126 patients. This is a sample according to the formula which is meant for a infinite population, very huge population. But here we are using a figure from a limited finite population, a limited population, which is 100 and 100 cases studied by Mr. Hassan. The majority of each were operated by the surgical registrars during the training program. So we have to divide this number, 126, this sample size according to the formula for infinite population, for very huge population. We divide it by the population, the limited population, the finite population in the study. If it is more than 5%, we have to apply a population finite population correction. If it is less than 5%, we consider it as it is and no need for any correction, if it is less than 5%. Now we have to divide 126 by 100 and multiply by 100 to get the percentage. It will be 126%, which is more than 5%. It is more than 5%. Therefore, we are going to apply finite population correction, which is very easy. No no problem at all. To use it for a limited population, finite population correction, we use the same sample size as 126, which we have calculated as if it was an infinite, as if it was a very huge population. We divide it by 1 plus the same number, sample size for infinite population equation, minus 1 divided by the total number in the study, which was 100. And if we replace the figures, it will be like this: 126 divided by 1 plus 126 minus 1, which is 125, divided by 100. 125 divided by 100, it is 1.25. Plus 1, it will be 2.25. And we divide 126 by 2.25, the result will be 56. This is the adjusted sample size for this finite, this limited number of patients, this population, limited population, finite population. Okay, so there is a difference. When we calculate it as if it is an infinite, very huge population, the sample size was 126. And when we correct it to this finite, to this limited population, we have to study only 26 patients. The sample size, the adjusted sample size will be 26. So the difference is large, isn't it? Very big difference. Why to use the finite population correction? Why? The finite population correction is the adjusts the sample size, that it adjusted the sample size precisely to fit the finite population, which is 100, the limited population, rather than the infinite population. The formula, the equation was meant for infinite population, but the correction is done to fit the limited population, which is finite population. And the use of this, when we study only 56 cases, it will save for us time, effort, and cost, and money, isn't it? And particularly if we are doing a prospective study or an experimental study. Usually in experimental study, we do not need a lot of numbers. And in prospective study, usually it costs a lot of time and effort. So by calculation, if we study a sample size of 56 and we document that we have used the figure so and so, and we apply the finite population correction, and if we document all these, the study will be 100% correct. So we should write, we used a 95% confidence level. From where we get this? Because we have used 1.96 z-value. That means it is used for 95% confidence level. We should write, we use 95% confidence level and a margin of error of 5%, that is 0.05. And we got this number. If you want a bigger number, we can reduce the margin of error, because it will be in the denominator. It will be in the denominator, down. And when we divide by a small number, we get a huge sample size. We can get in the E squared, the margin of error, 2% or 3%. Then we get a larger sample size. And with great precision, with great accuracy. We have to document all that. And we have to write that we calculated the sample size assuming an infinite, a very huge population. But because the population is finite, is limited to 100, we applied a finite population correction, and we ended with 56 cases as a sample size. If we document this, everything will be all right and it is correct. However, if we want also bigger sample size, we can use a bigger confidence interval. We can use a 99% confidence interval because it is in the numerator. We can use it because automatically the z-value will be big. It will be 2.576. If we want to use less confidence, 90%, then we use z-value. I spoke about this in the previous video, and we will use a z-value which is 1.645. So if we use a higher confidence level, and if we use 50%, which gives us the maximum variation, and I will demonstrate it after a few slides, and a small margin of error, we will going to get a high sample size. And all these methods are correct and applied, provided we are going to document all the steps in the study. Because they give power, the z-value gives power, and the margin of error, it gives us precision. Now, if we do not want to use this, and some are seeing that a lot of calculations and they do not want mathematics and these things, they can use one formula. And I had my previous video on Slovene formula. But in Slovene formula, you cannot use, it is built on 50%, built in the formula, which is not shown in the formula itself. And also it is built on 95% confidence, although it is not shown in the formula, okay? Yet, you should know the total population of the disease you are studying. And you get that number either from the medical records, you go and ask them and find from the logbook of the medical records how many cases they have admitted in the hospital in 6 months' time or in 1 year time. Or if it is, for example, trauma cases, you go to the emergency room and see how many patients were treated for trauma in the accident and emergency, in the emergency room, how many cases of trauma or war injuries has arrived and treated in the emergency room. Or if you are treating ICU cases, you go to the ICU case and see in the logbook how many cases of this type of disease admitted in the ICU. Or if you are studying certain pathology, you go to the laboratory and see how many specimens they have received from that particular disease. All these things, you get the number in 1 year or in 6 months from the hospital resources. And this will be the capital N, the population. The Slovene formula is meant for a known population size. Then you calculate this number, N, capital N, divided by 1 plus the same number, capital N, multiplied by the margin of error square. And you can decide for yourself the margin of error you would like to use. Commonly it is 0.5, it is 5%. It can be 0.4 if you would like, 0.3 or 0.2. Let us suppose we went to the medical record and asked them in 6 months how many cases of cholecystectomies were done in this hospital. And they said, we have the files of 100 patients. Then our sample size to study, to have a study in cholecystectomy will be this population size, which is known population size 100 over 1 plus 100 multiplied by the margin of error square, the margin of error which we want to use, whether it is 0.05, it is 5%, or 4%, or 3%, or 2%. And with this figure of 100, we are going to get about 80 cases. If you do not want to use the Sloven's formula, you can use Cochrane's formula. Now, the Sloven formula is for a known finite population size, known from the medical record or laboratory or emergency room or ICU or whatever. It is simple and easy and fast, and usually for small scale studies. And let me say like this, just a small scale studies. It is fast. It is based on 95% confidence, although it is not written on it. And it is based on population proportion of 50%, although it is not written it. Okay, this is from the statistical literature. On the other hand, the Cochrane's formula, with or without finite population correction, it allows you to change the confidence level. In the Slovenia, you cannot change the confidence level. It is fixed, 95% fixed. Means the z-value built in is fixed. There is no z-value for you to write. And the Cochrane, you have to apply a z-value either for 99% or commonly used 95% or less used for 90%. So it is allowed that you can change the confidence level. And it's a square, as I said before. And of course, you can change also, in both formulas, you can change the margin of error. That gives you precision. If you want a small one, you will get a bigger sample size. If you want a 5%, you will get a relatively small sample size. Also in the Cochrane, you can apply 50% as a fixed figure for the proportion, for the population proportion. You can write, we couldn't find a study for this to quote from it the proportion of incidence or prevalence or frequency of this disease or of its outcome. And we have used liberally 50% because it gives the maximum variation. And I will demonstrate that shortly. Now let me give 3 exercises. And among them, I will demonstrate the importance of 50% proportion. In this home exercise, I would like you to do it at home. Just code the figures and try to solve it at home. Calculate the sample size for a study in breast cancer, assuming infinite population. Means not necessary to apply finite population correction. Just assume it is infinite population. If you want to search for a study, if you search for a study, you will find the study of Dr. Ahmed. And if you would like to retrieve their manuscript, you will find, you can quote this digital object identifier here. And you will find that they found in their specialized breast clinic that the rate of breast cancer is 34%. If you apply this to the Sloven's, to the Cochrane's formula, you will get a sample size of 345, because the percentage size 34%. And if you use a liberal parameter proportion that is 50%, you will get the sample size 385. And the difference is not that big, because the difference between 38% and 50% is not that big. I will remind you with the formula again. It is a z-value square multiplied by the parameter multiplied by 1 minus the parameter divided by the margin of error square. Now to demonstrate that the liberal 50%, this figure 50% gives the maximum difference, the maximum variation, the maximum sample size. Let us take from the equation, from the Cochrane's formula, only the middle portion, which is the proportion multiplied by 1 minus the proportion. It is in the numerator on the top. If it is big, then it will provide us with a big sample size. If you consider 90%, and then 90% multiplied by 1 minus, it is 0.9. 90% is 1, it is 0.9 multiplied by 1 minus 0.9 will be equal to 0.9 multiplied by 0.1. Each has got a single decimal, and the result will be 0.09. The 80% will be 0.8 multiplied by 1 minus 0.8 will be 0.8 multiplied by 0.2, and the result will be 0.16. If we use 70%, the result will be 0.21. If we use 0.6 and 60%, the result will be 0.24. If we use 0.5, that is 50%, the result will be 2.25. It is the biggest, up to now, it is the biggest. It is the biggest difference. It is the biggest number, and it is in the top, in the numerator. If we use 40%, 30%, 20%, or 10%, the result will be less. It is 0.24, 0.21, 0.16, 0.09. So the highest variation, the highest difference, maximum difference will be when we use 50%. This is mathematics. This is mathematics. So the highest number will get in the numerator on the top to multiply this square by this number is the 50%, which is 0.5, multiplied by 1 minus 0.5. 0.5 multiplied by 1 minus 0.5. It will give us the maximum number in the numerator. And in the denominator, we can use the margin of error, which is E squared. We can use it as 5%, 4%, 12%. The smaller the figure we get, then the calculation will give us bigger sample size. I hope this is clear. Why we use 50%? It is made by statisticians. 50% is the standard, safe, and practical practice. 50% mathematically, P multiplied by 1 minus P gives the largest possible sample size. 50% is safe in absence of a study, if we couldn't find a proportion in any study. And it is easy to remember. 50%, which is written as 0.5, is conservative estimate that represent the maximum variability. It is commonly used, and if we use it, we do not need any figure from our side. We can just calculate, and the sample size will be fixed all the time. Let us take another exercise from exercise. Calculate a sample size for a study in gastric cancer or about gastric cancer, assuming infinite population. No need to perform finite population correction. If we are either we have to use 50% in our equation, in the formula, P multiplied by 1 minus P, and we know the z-value, and we know in the denominator the margin of error we would like to use. Or we can search for a study, and as I said before, we can find the study of Professor Ahmed Mohammed Hassan and his colleagues, and this was a digital objective identifier if you would like to retrieve that manuscript. And they found in their lab, as I said before, that the percentage or the frequency of gastric cancer among all tumors they received, not gastric, not alimentary canal tumors only, not GIT tumors only, it's all tumors, it constituted 4.5%. If we use 4.5%, we can study only 60. You do the calculations at home yourself, and you will get the result 67 cases sample size. If you use 50, because there is a very big difference between 50% and 4.5%, then you will get a bigger sample size, which is 384. And as I said, if we use 50, we do not need any figure from any other studies. We know P and 1 minus P according to the 50%. And we know the z-value 1.96 squared for 95% confidence. And we know the margin of error, which we are going to choose 5%, which is 0.05 square, or 0.04 square, or 0.03 or 0.02 square. Let us take a third and last example, and this is from the fact sheet of the WHO that reported the incidence means new cases, prevalence means existing cases. The incidence of colorectal cancer in Sudan was 6%. Now calculate sample size for a study in colorectal cancer assuming infinite population. Means ignore the finite population correction. You do this at home. You use the Cochrane's formula. Very easy. And use the figure 6%. It is 0.06 multiplied by 1 minus 0.06. And you know the z-value, and you know you are going to divide on what you have chosen as a margin of error, and you square it. If you use the figure 0.6 as incidence, which is a parameter, and the whole topic is on calculating the sample size based on population parameter, if you use the 6% as population proportion, then we are going to get a sample size of 87 cases. If we use 50%, we know all the figures now. The z-value, we know it 1.96, and we square it. And the e-value, we can take it as commonly used, as usually used, 0.05, that for 5%, and we square it. It will be 0.0025. And we use the 50%, which is 0.5 multiplied by 1 minus 0.5. And it will give you this number, 385. Very easy. The Cochrane's formula for calculation of a size using population proportion, it is used for the infinite population, for a very huge population. But if we are going to use a parameter or a proportion from a study, then the sample size we are going to get, we have to divide it by the number of patients in the study from which we get the proportion. And if it is more than 5%, we have to apply a finite population correction. If it is less than 5%, no need for finite population correction. Now, and you choose whatever you want to use as margin of error. So the figures are clear now. Either you use P from a study, the proportion, or you use it liberally as 50%. Very easy, very clear, scientific. It gives you power, since you are using Z value, means 95% confidence. It gives your calculation power, it gives the study power. And the margin of error also, it gives you more precision. The smaller the value, because it is in the denominator, you are dividing the number by the margin of error. The smaller the margin of error, the higher sample size you get, according to your study. If you are having an experimental study, you do not need much of sample size. If you want to do a prospective study, probably you do not need a very vast amount of sample size. The slogan formula is meant only for a known population size. Known population size, we get it usually either from the medical records, or from the laboratory, or from the X-ray department, from the ICU, from the emergency room, whatever. The source of the total population, or from the Ministry of Health, usually there is a source to give you the total population. And you use that total population and you divide it by 1 plus the same total population multiplied by the margin of error, and you can choose the margin of error you want. 0.5, it is 5%, 4%, 3%, or 2%, whatever you like, square. To this point, I will stop, and in the next video,